I want to show you a new draft design for file system interfaces for Go. Why would we want file system interfaces? Well, it turns out that the interface presented by file systems, that of trees of named resources, is a good abstraction for lots of different kinds of resources. At the bottommost level, the Unix file system abstracted away managing disk blocks so that programs don't have to think about this data goes in this disk block and this data that goes in this numbered disk block. And instead, we've got this much better abstraction for thinking about things as in having human-friendly names. And then building above that, we have file systems that abstract away which disk the blocks are in, so that you can have your files spread across multiple disks to get a bigger file system without having to think, oh, well, these files belong on this disk and these files go on this disk and I'm out of space over here, but there's lots of space over there, but that's not the right name, and so on. And then we have network file systems so that you can use the same files from lots of different machines and not worry too much about which machine they're on. And then at even more recent example, we have things like HTTP and REST, where really arbitrary resources can be presented as named paths with operations like get and put on them. And the really interesting thing about having an abstraction like this is that it lets you build tools that work on files, and those tools don't understand all the things the files really represent, but they still work for operating on them. So for example, the lowly Unix command cp that copies files, if you cp from one file to another, it doesn't care that under the hood it's actually moving disk blocks around. Or if you cp and it happens that the source and destination files are on different disks, cp doesn't know and doesn't care that bytes are moving from one disk to another. Or if they're on different machines, cp doesn't care that there's a network involved. And so having the abstraction lets us present different resources to these general tools in a way that the tools can work on lots of different things, and users can connect them in ways that are completely unexpected. The person who wrote CP almost certainly was not anticipating that CP would be used to copy files over encrypted network connections at some point in the future. Many years ago, Rob Pike and Ken Thompson built a whole operating system around this idea of presenting everything possible as files, and then having tools that understood files that then understood all the other resources. So for example, in Plan 9, because everything was presented as a file, if you knew how to mount the file system of one machine onto another machine, then you could get all the other machines' resources as well. So for example, if you can access another machine's files and use them, and the video camera or the monitor or the keyboard and mouse on that system are files, then sharing the file system over the network is enough to share the video camera over the network, or the monitor, or the mouse and the keyboard. When this was in the early days of the internet, when you weren't on the internet all the time, so if you wanted to connect your machine to the internet, if you wanted to actually use the internet, you didn't actually connect your machine to the internet. What you did was there was one computer that had a network interface that was actually connected to the internet. And you would import that computer's network interface onto yours in the /net location. And then all the programs that were opening and reading files in /net to use the network stopped getting your network and started getting the internet interface from the other machine. So that was our firewall machine, and it was the way that we actually shared the internet connection. And it also worked. You could import /proc from another machine and then debug with permission someone else's processes. And there were just tons of these unexpected connections that came out because we had this really strong abstraction of file systems and then tools that worked on them. And we can see that in the Go ecosystem, there's not quite the same opportunity there because we're not pushing quite so hard. But there is still a lot of opportunity to do some really good connecting and make things possible and easy that are really unanticipated by the people who are writing both the general tools and the file systems, because someone else can come along and say, I can use that file system with this other tool and do something really interesting. We already have some evidence, some strong evidence, that this kind of approach will work well in the Go ecosystem. And that evidence is the IO reader and IO writer interfaces and everything that's been built on top of them. when I defined those interfaces, I had worked on Plan 9, and so I really wanted to have that generality and that ability to build unexpected connections and bring that over in this much more limited example of just streams of bytes being read and written. And so, obviously you have basic readers and writers like operating system files and network connections. And those are the first two things that we, abstracted away with io.reader and io.writer. But then that opens the door to in-memory streams like bytes.buffer and io.pipe, or operations on streams like hash.hash, or pieces of protocols like the HTTP response writer, or the request body, or the response body. And then once you have all those different readers and writers, then you can build these generic composable tools that operate on them no matter what they actually represent. And so you have things like buffering for readers in buff.io, or encryption in crypto/cipher. You have stream writer and stream reader that encrypt as the data flows by. Or you have TLS-con, which is a netcon that has TLS applied so that the whole network stream is encrypted. And then you have these other operations like io.copy that can copy from one place to another no matter what the bytes are, just like the CP command. And then there's other ways to build readers and writers out of other readers and writers, things like multi-reader and limit reader and t-reader and multi-writer. So why not do this for file systems as well? Now, file system is a broader interface than just one method like read or write. And so we should expect that it won't apply as broadly as reader and writer do. But in the places where it does apply, where it's a good fit, you're connecting that much more functionality to general tools. And so it becomes that much more powerful in the slightly fewer cases where it does apply. We've done one file system interface in the past, and that was inside the program called GoDoc, which serves Go program documentation like on golang.org. And for GoDoc, we defined two interfaces. One was called file info, that was kind of the result of stat, and give you things like the file name and the file size, and that became os.fileinfo. And then we also defined a file system interface. The file system interface gave you these operations that GoDoc needed, but it was clear it wasn't really a good general purpose interface. And so while file info became a general purpose thing, os.fileinfo, file system just stayed inside GoDoc because it was obvious it really wasn't the right thing to present to other people. Now, separately, that was about 10 years ago that we were working on the GoDoc file system, and we just sort of put the idea of file system interface to the side. But separately, we would like to add support in the Go command for embedded files. And so we would like to have a way to connect those to other things in the standard library, and that means coming back to this problem of what should the interface be for file systems. Now, there have been past approaches to providing embedded files by lots of tools, and one of them is called Go bin data. And so here is what Go bin data provides. It provides a function called asset, which is like read file, and then asset info, which is like stat, asset names, which is kind of like read dir names, asset dir, which is also like read dir. I guess asset names gives you back the entire file system, and asset dir only gives you one directory. And then there's restore assets, and restore assets' job is to copy all the embedded assets back out of the binary into the local file system so that programs or other packages like nethcp and text template can read them using the os.file API because they don't have any other way. And so, when you see this, when you see restore assets in particular, you should wonder, well, wait, why do we have to write everything back out to the operating system file system just to get it back into these other tools? Shouldn't things like nethcp and HTML template be able to consume embedded files directly? Well, yes, they really should. But if you're going to go to the trouble to do that, should the new API really just be about embedded files, or should it be about general file systems? And the point of this draft design is to answer the question of what would it mean to do general file systems so that if we want to make embedded files work with these packages, we actually end up with a much richer functionality for the same cost by generalizing. So nethcp actually has a file system interface. This was the second file system interface that we did after GoDoc a couple years later. And HTTP defines, again, the file system interface that it needs. And this one is much simpler, which is nice. It just has the open method, and open returns a file. but file is itself an interface defined in HTTP. And an HTTP file needs a close method, a read method, a seek method, readdir, and stat. And this is fine for HTTP. It really does need all of these, at least from some of the files that it accesses. It's still probably a little bit too much for general purpose use, but it's pretty close. The main problem is that you've got most of your files are not directories, and it doesn't really make sense for them all to implement readdir. Most of your files, or your directories, don't need seek. In fact, many of your files may not be able to implement seek, but HTTP needs seek, so it's important for HTTP, but it might not make sense in a general interface. And then on top of that, we have this nit that like readdir really needs a capital D, and it doesn't have one, and it doesn't have one because the one in os.file didn't have one. But if we're going to make an interface that we're going to encourage lots of other people to write against and implement and accept and use, and we're going to be making changes anyway, like why not actually fix the spelling of readdir while we're here? So the problem then is like we want to define a general file system and file interfaces that will help connect these consumers, these general tools, with implementations of the file API. And we want to do this for consumers and implementations that exist inside the standard library and that exist outside the standard library. And can we do this? Can we actually build an interface that works well enough? And we really hope that we can, and this draft design is our best attempt to do this so far. And we want to share it with you and get feedback. Just to be clear, this is a draft design. This is not a proposal. If adopted, this would be a fairly large change. It's definitely user visible. It definitely requires changes to documentation, and it definitely affects multiple packages. All the consumers inside the standard library, all the sources of file systems inside the standard library, but then all the ones outside the standard library, and all the tools that people might be able to write afterward. So it has wide ecosystem effects. And so we want to get feedback about this draft design without the pressure of the proposal process. If the feedback is overwhelmingly positive, or if we make changes and then the feedback is overwhelmingly positive, then it's possible that this could get proposed and then become part of Go 116, or it's possible that we'll just say no, this isn't worth doing, and we'll find some other way to do embedded files if those happen. Or it's possible that we'll need more time and it'll happen in a later release. And we don't really know, but we're not at that stage yet of deciding that question. We're just trying to get feedback about this design, and then based on the feedback, we'll iterate. And when things are ready, then we'll try to figure out when makes sense. So the basic design is that there's a new package, io/fs, and that defines two interfaces, fs and file. And then having defined that package, we make adjustments to the standard library in archive zip, the two template packages, NetHTTP, and OS. And then in addition to that, there's a separate draft design for embedded files, and the embedded files also implement fs so that they can hook into all this generality that we're introducing. But that's the subject of a separate video that I'll link below. The fs interface is in the new package that you import as io/fs, and it defines the minimum requirements for a file system implementation. And that minimum set of requirements is just an open method. And open returns a file, just like we saw in HTTP, but this file is the file interface defined in fs. And so an fs implementation may also provide other methods if it wants to provide additional functionality or optimizations, but the only required method is open. And we'll see examples of some of these other methods later. The argument to open is a path name, and the path name is a /separated name like x/y/z.jpg, and it is always /separated, even on Windows, just like URLs. There is no leading slash in the name, which makes clear that the paths are relative to something that you're not seeing, that's not specified, which is which file system are you passing this name to. There's no dot or dot dot allowed in the names in order to simplify the implementation, so they don't all have to worry about that. With one exception, the root directory, because it's not slash, is called dot, and so you can open dot to list the top level files and directories. And then open returns a file, and there's a separate file interface, which again defines the minimum requirements for a particular implementation. And those minimum requirements are stat, read, and close methods. and those have the same meanings as for os.file. Now you might have noticed that the file interface does not provide a way to read a directory. And so there is separately a readdir file interface, which defines the additional requirements for a file that itself represents a directory. And so readdir file is an interface that includes all the file methods, but adds readdir. And again, we're going to fix the spelling of readdir and capitalize the D in dir before we make lots of other code implement this. Now, readdir file is an example of a pattern that we've been doing in certain ways from the beginning, but that we've never given a name to. And I'm going to call that pattern the extension interface. And the extension interface is you embed a base interface, and then you add some more methods to it. And so a readdir file is a file with a readdir method. And you can kind of see this if you squint in some of the earlier things we did. We didn't design them this way, but they actually match this design. Things like read writer. A read writer is writer with a read method. Readdir file was an example of an extension interface for a file. We also can make extension interfaces for the FS interface. So here's one. A read file FS is an FS with a read file method that lets you just get the file's bytes directly in one call without having to open it, read all the bytes, and then close it again. In addition to defining the readFileFS interface, we can also define a function, readFile, that takes a file system and a name and checks to see, does this file system implement readFileFS? And if so, call the readFile method, because that will presumably be faster or at least simpler. And if not, fall back to some sensible behavior. In this case, we open the file, call read repeatedly, and then close it and return the data. That example of the readdirFS interface and the readdir helper function is a pairing that we've actually been doing for a while, but without giving it a name. So I'm going to call this the extension pattern, which is when you have an extension interface paired with a helper that uses that interface if it's present, if it's implemented by the argument to the function, or else does some sort of sensible fallback with what it has available without those extra methods. So we've been doing this kind of thing for a while. We didn't have a name for it, but now we have a name, the extension pattern. So one example of a time that we did this in the past without the name is in the writeString helper function in I/O. So I/O defines a string writer interface, which is almost an extension interface, not quite, I'll come back to that. And then writeString, the helper function, checks to see if the argument, which is just a writer, is also a string writer, and if so, it uses that to implement the functionality directly. And otherwise, it falls back to just calling the write method after converting the string to a slice of bytes. Now, the only thing that is not quite fitting this pattern is that string writer is not quite an extension interface because it doesn't embed writer. If we had done this, if we'd done this, this would be a proper extension interface. But we didn't. The write method is not there. And that kind of makes sense for string writer because if you've done the conversion, you check that a writer is a string writer, then you don't need the write method anymore because writeString essentially completely obsoletes write for your purposes. But if there's multiple methods involved, like there are in file, then adding one more method doesn't necessarily give you everything you need. And so for these larger interfaces like FS and file, it makes sense to keep access to the originals as well as adding the new methods. So here's another example of applying the extension pattern and an extension interface to FS, and it's stat. If you want the ability to just stat a file without opening it, the same way that the os.stat function does, then you can, in your FS implementation, provide a stat method that just takes the name and does the stat operation. And then the FS package provides a helper, fs.stat, to which you pass a file system and a name. And if that file system implements statfs, it will use the stat method directly. And otherwise, it does the obvious thing. It opens the file, calls stat, closes it, returns the result. We do this again. Here's readdir. So if you have a file system that can read from a directory, read the whole directory all in one shot without having to do an open and successive reads and then closing, then you can provide a readdir method. Now here's an example of a place where the extension pattern doesn't really apply. and that's the helper walk. So we clearly want an equivalent to filepath.walk for arbitrary file systems, and that should be provided as fs.walk. But there's no walkfs extension interface in the draft design. And the reason is that there's almost no reason a file system would need to implement that. Things like read file and read dir, the implementation of the file system may have a more efficient way to do that without having to go through opening and individual reads and closing. But for walk is actually very complicated code. It's pretty subtle. There's all these corner cases. And so it makes sense to just have the one copy and not have individual file systems have their own buggy copies. And there's no compensating reason you would allow individual file systems to have their own buggy copies because there's not really any optimization opportunities. Walk's job is to walk over the file system, call the callback function for each file in the file system, and it's perfectly efficient at what it does. There's really nothing that could be made faster from internal access to the file system except for the operation of just reading the directories. And so if you want to make walk faster, you implement readdirfs. You don't implement walkfs because there is no walkfs. On the other hand, here's another extension that's a little bit like walk, but the calculus comes out on the other side. And so for glob is like filepath.glob, where you pass a pattern like star.go, and it tells you these are the files in the file system that match star.go. And so there's a helper function, fs.glob, and you pass a file system and a pattern, and it gives you back the list of files that match that pattern. But in this case, it does make sense to let file systems provide their own top-level glob function that the glob helper, fs.glob, will call if it's present. Because there are very significant optimization opportunities. And the most significant one is that if you have a file system that all the actual files are across a network somewhere, and you glob something like star/star/star.go, and there's not that many Go source files in the file system, then it makes a lot of sense to send that one pattern across the network, have the implementation across the network, do all the file system walking locally, find the one or two Go source files, and then send back that list. Instead of, the fallback behavior would be to read the contents of every directory on the remote file system and then filter it down to just the .go files. So here, if a file system knows that it can filter faster in a different way than just reading all the directories, that filtering will be a much faster operation, then it should implement glob as a method on fs and then make that faster. So this is different from walk because walk did not have an optimization opportunity like this. So it really didn't make sense to expose the possibility of different implementations. One of the really nice things about this design is that we don't have to do all the extension interfaces in the fs package. As long as all the extension interfaces agree on the two names fs.fs and fs.file, the rest of the details can be done in other packages. So for example, if you wanted to add to your file systems the ability to call a rename method to rename files, and you define it like this as an extension interface that embeds fs and then adds the rename method with the same signature as os.rename, and then you complete the extension pattern by defining the helper func rename that takes the file system and the old and new strings and then checks to see does this file system implement the rename fs interface, and if so, use it, and otherwise provide a reasonable fallback. If you do all this, then someone else who's decided to add a rename method just independently that code will interoperate with your package. And furthermore, if you did this and someone else needed to rename fs, those two interfaces come out exactly the same, so that a third package can implement both of them at the same time. And so all these different extensions interoperate provided everyone agrees about the name fs.fs and also fs.file. As another example, suppose we wanted to have writable files. Then anyone who wants writable files now can define a third-party extension interface, openFileFS, that embeds an fs, adds the openFile method with the signature from the OS package, and then also defines a helper function, openFile, that looks for the extension and uses it if present, and otherwise, if it's being opened for read-only mode, then it could just call the regular open method, and otherwise, it'll have to return an error. And then you can also have a create wrapper that checks for open file, or that calls open file, which will do those checks. And Supposing you did this, and supposing someone else did this, some third package written independently of those two different but common extension interfaces could implement OpenFile as a method on FS following the example of OS, and it would automatically be compatible with both of those. And if at some point in the future we decided this was worth having in the standard library, we could copy this code over, and again, it would still be compatible with the standard library version and all the external ones. And the reason that all those interfaces are compatible is that the only types that they mention are types that are already defined in the standard library, specifically fs.fs and fs.file. And this is what I mean by they all interoperate. And the nice thing about this is that as long as we agree about fs.fs and fs.file, then we don't have to do everything in the standard library. We can start small. We can focus on just read-only interfaces for now. We can learn how well this works before we expand to other things. Speaking of the standard library, in addition to just defining the interfaces, we want to integrate the use of FS well into the standard library, the same way that reader and writer are integrated well. And so we want to update file system implementations to satisfy the FS interface. And we want to update file system consumers to accept the FS interface, or add equivalent code that does accept the FS interface. So in the standard library, there are two implementations, archive zip and OS, and there are three important consumers, the two template packages and netHDP. In addition to these, there's also consumers of the direct OS package that we've already seen equivalents for. So for example, filepath.walk and filepath.glob and ioutil.readFile. Those all become helper functions in FS. So instead of using those, you call the ones in FS. But these are examples of places where the surrounding package is so complex and it provides such different functionality that it makes sense to put the FS hooks directly into that package instead of doing it in package FS. First, we have some changes to OS itself to make the rest of the standard library changes fit a little bit better. If you're going to implement the fs.fs interface, you shouldn't also have to reach in and import OS just to get these concepts that are core to the file system interface. Those concepts should be in the FS package itself. And those things are things like file info and mode dir and those other names that you have to use to implement the FS interface. And also, for OS to provide any FS implementation, it has to import io/fs in order to mention the name file, which we saw before is so important. And so you can't have OS importing iofs to get file and iofs importing OS to get names like file info and mode dir. You have to put them all in one place, and so that one place is the iofs package. So we're going to move these general file system concepts out of OS into iofs and leave behind type aliases and forwarding constant and variable declarations so that all the code using OS still works, but the official home for these concepts now is in the FS package. Now, originally, even things like EOF were in the OS package. And when we did the run-up to Go 1 and rationalized a lot of this stuff, we moved os.eof into IO, becoming io.eof. And we talked about whether to move file info into IO as well. And it didn't really make sense that file info would go into IO, which didn't have anything to do with files. But it didn't make sense to have it in OS, where it was this general purpose interface. It wasn't only about operating system files, but we really didn't have a home for it. Now that we do have a home for it, it makes sense to move it to that home. The other change we need to make to the OS package is to make os.file implement fs.file. And the only thing we have to do is add a readdir method with a capital D, which will just wrap the readdir lowercase d method. In addition to that change, we want to add a proper FS implementation so that code that wants an FS can get one that's backed by the operating system. And so there can be a new function, dirfs, that returns an fs.fs implementation that presents the files in the subtree rooted at a given directory. So it provides access to that directory and the subdirectories, but not things in the parent directories. And again, I just want to note that to do something like this, to implement dirfs, the open method on whatever the implementation of dirfs is has to import io/fs to refer to the file type. And that means that iofs can't go back to OS for things like file info. So all of that has to move in order to have any FS implementation in OS. In addition to it having to move anyway, it just fits better into the gestalt of the Go standard library if we have the general purpose abstract I/O operations all defined in terms of types that are in I/O and IOFS and not reaching into OS. We also need to make some changes to the HTML template and text template package so that those packages can read templates from an arbitrary FS implementation in addition to the functionality they already have to read templates straight from the operating system. So to read from the operating system, these packages have a parse files, which takes a list of file, and they have parse glob, which takes a single glob. And those are both top-level functions and methods on the template type. And so to add support for the FS, for reading from an FS, we combine those two into a single parse FS that takes a list of globs and then matches those globs and reads the equivalent files. And we think that we can do this because essentially every file name is a glob matching only itself. And so it makes more sense to just have this one function that takes a list of globs than to have the two different functions that take a list of file names or a single glob. We also need some changes in NetHTTP. We already have the HTTP.file system and HTTP.file interfaces that we saw before, and there's this helper function, file server, that converts a file system to a handler. And those all have to be left alone. They'll keep working. They're never going to break. That's fine. But we also want to add something so that HTTP can directly consume this general purpose FS interface so that anyone implementing FS anyway will automatically work with HTTP. So we're going to add a new helper function called handlerFS that takes an FS and turns it into a handler. Now, this function name doesn't look anything like func_file_server, but honestly, I can never remember which one of file system and file server is the function and which one is the type. It was kind of a cute name at the time, but it really hasn't stood the test of time. Whereas handlerFS is exactly like handlerfunc. You pass handlerfunc a func and it returns a handler. You pass handlerFS an FS and it returns a handler. It's a much easier name to remember. Now, if we'd done FS earlier, and if we had gotten it right, which is a big if, then we wouldn't need file system in NetHTTP. But we didn't do it that way. That's not the way things played out, and that's just going to stick around for forever. And that's fine. It's totally okay. Now, I want to point out there is an untype checked requirement here in the handlerFS function. And that untype checked requirement is that when you open a file, when fsys.open returns a file, that file implementation, if the file is a plain file and not a directory, must have a seek method, and that seek method must actually work. And the reason the seek method has to work is that an HTTP client can connect and ask for a specific range of bytes from the file. And so to get to those bytes, the HTTP server needs to be able to call seek to jump straight to the bytes instead of having to read forward until it gets to the place and then throw away the rest, because that would be very inefficient. And so if it doesn't have the seek method and it gets a range request, the HTTP server is going to send back a 500 or some sensible error. And this is called out in the dot comment for handlerFS, but it's not something we can check in the type system because all the implementations need to agree on the use of the specific interface file and FS, which don't lead to a seek method. The file doesn't have a seek method, and FS is open, returns a file. And so this is an example of the tension between defining a general interface that works for lots of consumers and lots of implementers and lets you cross-connect things in interesting ways, and code that can be maybe wants to be more specific in the type system about exactly what it wants. Because the cost of that extra specificity is that you lose some of that generality. And so in the HTTP.file system interface and the HTTP.file interface, this requirement is made explicit, but that makes the interface less useful as a general interface. And so I just wanted to flag this tension because there's always that tension between having a general purpose interface, even like reader and writer, and having more specific requirements, like some things that take a reader also need a seek method or are more efficient if there's a read byte method. And so we have this example happening all the time already, but I just wanted to call out that it comes up here. We also want to make some changes to archive zip. A zip file is essentially a small little file system full of compressed files. And so we want to make the zip.reader type implement fs.fs by adding an open method. And so now we can load templates from a zip file. We can call openReader to get the zip file, ZFS in this example, and then we can pass ZFS to template.parsefs and say, find all the .temple files in that zip file, parse them, and give me back the template collection. And it's worth pointing out, even though you can get to a specific file in the zip file efficiently, because there's a table of contents written that's just a list of all the files in one place in the zip file, you can't get to a specific point in a compressed file efficiently, because the compression algorithm is a streaming compression algorithm, and the only way to get the decompressed, second megabyte of a file is to read through the first megabyte and thereby initialize the decompressor the right way to process the second megabyte. You don't even know where the second megabyte starts. And so the files returned by the zip reader's open method do not have a seek method. And that's fine for template. Template doesn't need to seek, it just reads the whole file. And so you can pass your zip file, the template parser works great. But as we saw before, the HTTP server really needs seek. And so if you try to call http.handle with the zip file, once you convert it to a handler, that will work. It will type check and it will run. That line will run. But when you go to fetch a file from the server, you'll get a 500 error if there's a range request because it doesn't have a seek method. And so this is just, again, continuing that example from before about needing seek and not having that directly in the type system. On the other hand, it would be easy if you really needed to be able to serve directly from zip files, then you have to be able to serve range requests. And so you either have to, you basically have to put them in memory somewhere and then serve from the in-memory copy, because then you can seek, or you'd have to recompress them with a different compressor that supported seeking, but standard zip files don't do that. So probably the best thing to do is to just have them in memory. So you could build a nice little file system adapter tool, which here I'm calling the function cachedfs. And what this hypothetical cachedfs would do is that it would take a file system and return a file system, the same way that things like limit reader takes a reader and returns a reader, or buff.io takes a reader, returns a reader. And this would be like a buffered fs, except it would buffer the entire file in memory the first time you open it. And then thereafter, it would be able to just serve seek requests based on the in-memory copy. And so then if you had this cachedfs function, which you could write fairly easily, then you could pass that to handlerfs and to handle, and then be able to serve from zip files. But here the need for seek is satisfied by this separate piece, so that you can still have reasonable file systems that don't have seek, but if you need it and you're willing to pay the cost of getting it, then you can do that. So it's worth pointing out there are no changes to archive tar. Because you can't implement open efficiently. Unlike a zip file, in a zip file there's a list of all the files in the archive that's written at the very end, which you can just read through to find a particular file. In a tar file, each file, it begins with the compressed data for each file is preceded by a header that has the file name. And if you want to find out the list of all the files in a tar file, you just have to read the entire tar file, one record at a time, and just collect all the names you see. And so there's no efficient way to implement open to jump to a specific name. And so when there isn't an efficient way to do something, we tend not to add a method for it in the standard library, because it kind of implies that we have a good way to do this. And if you wrote a loop that looped over a tar file calling open and readdir and things like that, it would be incredibly inefficient, or we'd have to spend that first open would have to do a lot of work to essentially read the entire file and build some sort of in-memory index. So it's totally fine for a third-party package to implement that sort of thing, just like it would be fine to have a third-party cachedfs. But it's not something that we're going to put into the standard library, because there's an implied efficiency that just we can't actually satisfy. You might wonder, why should we do this now? We wrote our first file system interface in Godot over 10 years ago. We've talked about it off and on since then, but why now? And there are a few answers. One is that we finally have a design that we think is actually the right design for a file system interface. And since we have something that we think is the right design, we want people to use it. We think that having that out there and for everyone to agree on will hopefully enable these generic composable tools and enable new interesting file system implementations, things where you're presenting resources as file system trees. And that will hopefully make Go packages more useful with each other and be connected in interesting ways. One specific implementation that we have that we would like to be able to connect to things like the HTTP server and the template package is little trees of embedded files within Go binaries. And there's a separate draft design for that, as I mentioned. It's linked below. And if we're going to do embedded files, then we should make it so that the most common use cases for embedded files at least in the standard library, which are serving them over HTTP and parsing templates, they should work. And we could add direct support to HTTP and template so that they can accept a set of embedded files as a concrete type. But it seems like it makes more sense to, if we're going to add something to those packages, to add something where they just take an arbitrary file system and they can take files from anywhere. And then hopefully other people will produce other interesting anywheres to present files from. So just as a few examples that pop to mind, etcd is an interesting key value store, but ultimately is sort of like a file system that provides interesting semantics in distributed systems. You can imagine modeling the etcd store as a FS. Things like cloud storage are obvious file systems. They use file paths already, and they use tools that pretend that they're file systems. So you can make that into an FS implementation. And then you can imagine layering, like the cached FS that was the in-memory file system, or in-memory layer that provided seekability for files that couldn't be seeked. You could imagine having in-memory layers like that for things like encryption. So maybe you'd have a zip file full of encrypted files that maybe you're loading from somewhere where you don't want to store the secrets, and then above that you put a decrypting layer, just like we have decrypting layers for readers and writers, so that then the ultimate reader of those files gets the decrypted copy instead. And once we create this interface, we don't really know where it's going to go. We didn't really know where reader and writer were going to go when we defined them over 10 years ago. We just knew that that was a really important concept, and that if we all agreed on the specific interface, that we could really build interesting stacks and layers of things and interesting implementations on either end and interesting consumers. And the same thing actually happened with http.response, not response writer, http.handler, where people started building things on both sides of handler. There were interesting new handlers, like the file system server is an interesting new handler. And then we had interesting new things that called handlers, the sort of middlewares for HTTP that did interesting things in the process of serving the requests. And so by defining this FS interface, we really hope that we're enabling another interesting place to combine things that will lead to things we haven't even thought about yet, and that we haven't imagined, but that will make things powerful by having these agreed upon interfaces that unleash a lot of creativity. Another question you might ask is, why is this not in golang.org/x? Why put it in the standard library? And the purpose is partly to help connect implementations of file systems to things in the standard library, like archive-zip and NetHTTP and HTML template. And so we can't do that if the package that all of these things refer to is not also in the standard library. And so if we're really going to do this thing that helps tie together pieces of the standard library in interesting ways with other unexpected implementations, that has to be in the standard library as well. Even if we had some sort of trick way to put it in golang.org/x and have the standard library refer to it, at that point it is part of the standard library. It's part of what you have to know to use the standard library, and so it might as well just be in the standard library. To wrap up, again, this is a draft design. It's not a proposal. We're trying to get feedback about this before we go into the main proposal process. The overall design, the core piece, is a new package, io/fs, that defines the FS and file interfaces, along with this story for how you extend these interfaces if you want added functionality and what the patterns are for getting more than just this basic read-only file system. And then, in addition to defining that package and how it gets extended, we want to make sure we integrate that well into the standard library to allow connecting pieces that consume files to any file system, not just the operating systems. And also to allow things that consume general file systems to get at things that today are presented as only standard files, like OS, so os.dirfs. And the first really new use of this that we'd like to also put forward, there's a separate draft design video, is Go command support for embedded files and binaries. And that's a separate video linked below. For this draft design, we have a full doc that is at the URL there, and we're going to run a Q&A on Reddit. We're using Reddit instead of GitHub because Reddit will thread messages so that if someone asks a question, you can see the responses to that question easily without having to skim through all the messages there. And similarly, Reddit shows you a lot more of the messages when you first load the page, whereas on GitHub, when you load the page, if it's a long conversation, it hides nearly all of the conversation which leads to a lot of duplicated comments. And then for the embedding draft design, there are links to that as well. Thanks very much for watching, and we're looking forward to your feedback. Have a great day.